Put your hands together for Waikin. I don't want to blow his horn lah, okay? But you heard of Lao yet? Yeah, okay.
Get your slides up. This is forward. Okay, I got my notes here, so...
Okay.
Okay, hope I have enough hands.
Are you guys all going to the toilet together? Okay. Do sneak in back in the middle. Yeah.
Hey, use a different photo. So hi, I'm testing. Can you hear me? Okay. Hi, I'm WK and I'm from OnApp, and I built a CDN. So today I'm going to show you how we built it and some of the key decisions behind it and some of the key components as well. So hopefully you can go home and build your own one if you want. Okay. So first of all, I want to show you a chart. It's this mysterious drop in traffic that we saw right over here. And I was wondering, like, is it a problem on our side, or is it a problem on the customer side, or is it even not a problem at all? So we found out that it's actually related to the World Cup. So if you look at the date, July 13th, World Cup final, 3 a.m., 3 a.m. That's your first half, second half, and extra time where, Argentina lost. And it's just one of those strange patterns you see sometimes. So I'm going to talk a bit about the basic concepts of a CDN. So is it clear if I go there or here? Okay, I'll just go here. So let's say you're the web guy. And you set up your CDN site on your CDN provider's admin thing. So your CDN provider's admin thing then needs to go and provision your CDN site on their DNS servers and on their CDN-H servers, which do the delivery. Your visitors will then try to access your site, and they will look up the DNS entries for your CDN site, and then it can proceed to download the stuff from the CDN-H server. So where OnApp fits into this is that we write software for hosting providers to make their own CDN. We run the admin thing and we run the DNS servers, whereas our customers would run the delivery servers. And the web guys would be their customers, they won't be our customers. And we also, next, come on. We also have a federation feature because it's sexy. Federation lets our customers expand their CDN delivery footprint by using other OnApp customers' H servers. So if you're a provider in Kuala Lumpur like Exabytes, you could, and you don't have presence in America or Europe, you could just get bandwidth from them through our federation. Okay, so that's a map of where we have, where our customers have H servers around the world. So we pretty much cover North America, Europe, and Asia Pacific, and one lonely server in South Africa somewhere. So moving on, talk about development and a bit of operations. So we have a personal CDN environment called CleanDev. It runs about 15 virtual machines because we have a habit where we run every service in its own VM. We standardized on using Ubuntu 14.04 for CleanDev because it turned out that we're running something called Vagrant and LXC. So Vagrant lets you create virtual environments quite easily, but it's not so easy when everyone's running different versions of Vagrant and different versions of LXC. After the developers have completed their work, they can then merge into the alpha environment where we have a bunch of cheap PCs running in our office, like 2,000 ringgit a piece. It's way cheaper than putting it on the cloud. And the developers would integrate here and make sure that everything works. So then we move on to beta, which is the pre-production environment for QA. It's pretty much the same as alpha, except that it runs on a public server somewhere, so that we can actually do CDN delivery testing with actual servers on the internet. And finally, we have Omega, which is hosted in Europe, and we have some other supporting infrastructure around the world, which I'll get to later. Generally, we run our setups on bare metal servers. It's kind of boring, but it's what we do, and it works. We get them lots of RAM and SSD, and we basically virtualize things ourselves. So if you want to go down the same path, I would recommend you to find servers with IPMI so that you can administer your servers remotely. So things like hardware reboot and hardware console and remote OS installation is things that we really need to make this as good as cloud for us. We're currently on Debian 6, transitioning to Debian 7. Our servers generally have 1 gig ports because we like to be able to burst for things like backups or file transfers. I mean, 100 megabit is kind of like last decade, and I think your SD card can probably transfer faster than 100 megabits. So just don't settle for it. We have 10 gig ports for some of our DNS servers. Reason for this is that if we do get DDoS, having a bigger pipe would increase the point where they would saturate. Okay, on configuration management, almost everything that runs on our servers are configured with Puppet. So there's about, I think, 140 to 150 virtual machines altogether. So for us, we really value reproducible deployments because we have those 3 to 4 different environments as I showed you just now. So we want to make sure that when we develop, we want to try to develop with deployment to production in mind. So everything should be kept as similar as possible from start to the end, and reproducible so that there's no mistakes that can be made along the way. So just an example, the definition for our Omega environment is about 1,500 lines of code. It describes all the servers, all those 150 servers, and everything that's running in them. And it's a text file, and the nice thing about text files is that you can use whatever you're currently using for managing text files with them. So for us, we use JIT, specifically Bitbucket, and we can use it to peer review, to branch off any changes we make. So let's say we want to introduce a new feature to a server, we could create a branch and merge that to alpha first and test it there, and after that we would merge that onwards to our beta and omega environments. And we can do this in any order because it's going to be a feature branch. So if something doesn't work out in alpha, that's fine. We don't need to push it to beta immediately. I put up a screenshot there of one of the commits from my staff. So he's just adding a package to be installed on all servers. And you can see a few key things there which establish this. It's established a paper trail. First you see who made the change, what time he made it, and why he made it, and also the ticket that he tagged it to. So all this is very important for accountability, and also because we want to know who broke the server, right? Every time. Okay. So our CDN admin thing. Our core API is written in Java, and it's exposed over XML RPC. I know XML RPC is not sexy. It's XML and it's super bloated, but it's what we use on day one. And I think JSON RPC wasn't around. I might have considered using JSON RPC instead. Then we use Python a lot in our company. So We use it mainly for like backend plumbing. For example, if you want to create DNS zone files or the Nginx configuration files, we will use Python to do that kind of thing. RabbitMQ, which Gareth mentioned just now, we use it somewhat like an inter-process communication bus between the different parts of the system. In addition to what Gareth said, another good thing about using a queue is that you get to monitor the queue length, so you know when you need to add capacity. Because if you don't, then the queue will keep growing and not shrink. So monitoring queues are an essential part of what we do as well. But RabbitMQ is not completely infallible. I know it runs Erlang, which is super sexy, but it still needs to be treated with respect. So we use RabbitMQ with durable queues, which means they need to persist the messages on queue to disk. And if you happen to run out of file descriptors, well, you sort of fuck up your RabbitMQ's amnesia data store, and it can fail catastrophically, which it has for us a few times. So we store our data in MySQL and MongoDB. For Mongo, well, I think we're not really using it the right way. Not using it for the right use case and for the right kind of data. We're storing very tabular, structured data in Mongo, and I think it just adds a lot of overhead and makes the queries much more complicated to write. On our CDN H server, which is the server that does the actual content delivery, we use Nginx and Wowza. Nginx is for HTTP objects and also for HTTP pseudo streaming, and Wowza is for live streams and those pure streaming protocols like RTMP, RTSP, HLS. We use the LVL module for Nginx. It's a really cool module. It lets you hack Nginx in many interesting ways. So whereas in the past you might have to create very complicated configuration files or even hack the Nginx code itself, so now you may be able to do that in Lua. And Lua is quite a simple language to learn. So just an example of what we do with it. Instead of defining virtual hosts as in Nginx server blocks, or in Apache it would be like virtual host blocks, we define everything in a JSON file. So the JSON file would have your CDN site's name, aliases, your customer ID, and your origin. And it's very, very compact compared to defining a full virtual host, which can take about a few tens of kilobytes of memory, which doesn't sound much, but when you have a few thousand sites on the server, it takes a very long time to It takes a very long time to parse the config file and takes hundreds, possibly of megabytes of RAM to have them in memory as well. For monitoring, we have not just in the H server, so it does some rudimentary monitoring of the local processes, checks that the port 80 is up. If it's not, then restart Nginx. Checks if there's enough free disk space. If there's not, then restart it. Sorry, not restart it. Just try to free up some objects from cache. So basically, we're trying to do a bit of self-healing with Nagios, so that a problem can be controlled at an earlier stage without taking the whole CDNH server down. Manan and CollectD I'll explain a little bit later. Finally, we have Puppet, which would provision the H server. So we can provision any Debian server from scratch. So our solution doesn't just work on the images that we provide to our customers, but also to any any bare metal servers which have Debian installed, which is great for some of our customers who prefer to run on bare metal. The kind of plumbing that would be used here would be like, let's say someone creates a new CDN site. The configs need to be pushed to the H server. So we have a script, a daemon, which sits there waiting for this, and when it gets a message that, hey, there's new configs for you, it'll go and rsync those configs over. Also, workers to purge and prefetch files on the edge server. So purge is like, you have content on the CDN that you don't want there anymore. Maybe it's like it's outdated, or maybe for compliance reasons you need to remove it. So we have plumbing to do that kind of thing as well. Next up would be it's going to be about DNS. We run something called Power DNS. It's an extensible DNS server, and why I say it's extensible is because it gives you 2 APIs, 3 or 4 APIs actually. So one of them is the C++ API, and another one is a very simple text-based protocol. It spawns your process, your plugin, and it'll send the query into your process as text, and your process will reply in text as well. And it also now supports an HTTP RESTful API. So we wrote a plugin for Power DNS which would answer these DNS queries dynamically based on your CDN site's footprint. Footprint is basically which POPs are serving your CDN site. For us, we're very flexible. We let you determine which locations exactly serve your CDN. It's not a one-size-fits-all solution. The edge server health and load. So health would be like whether it's up or down, and load is how much CPU it's using, or how much I/O and network bandwidth it's pushing out. And finally, the estimates of the edge server distance to the visitor, which is well, let's say you have a server in Kuala Lumpur and United States, and you're going to be your visitors accessing it from, let's say, Singapore. So which is a better server to route the user to? So logically, it may be Kuala Lumpur or may not be. So we need to estimate this distance, and we do this with maximize IP geolocation, and also we have a latency model where we ping many IPs around the world from our edge servers and use some machine learning to build a model to try to estimate what's the ping from the edge server to the end user. And we have DNS servers around those places with 2 anchor providers, SoftLayer and Voxelity. We chose them because for Voxelity, we chose them because they use Telia everywhere, which we need to standardize on one upstream provider, and SoftLayer because they are awesome, and they also have the same kind of arrangement, 1 single or 2 single transit providers around the world. And we also have like smaller local DNS providers. And our DNS is load balanced and routed using BGP Anycast. What this means is that we would use BERT, which is a software BGP daemon, to establish a BGP session with our provider's routers. And over here, we would announce the IP prefixes for our DNS servers. And we announce the same IP prefixes at all those locations. So I think you guys would know what unicast means, which is that if I were to send a packet to an IP, it would arrive at exactly one destination. Broadcast. Okay, how many slides do I have? Your phone's in Japanese. I think I have three or four more slides. Okay. So what was the magic word again? So are you still with me? It's not. Okay. Are you still with me? Not. Okay. Okay. So so your ISP's routers will determine what's the best path to our DNS servers. So from here, from DMNet, it's going to go to the Singapore DNS server with about 15 milliseconds of latency, and from another provider in Rotterdam, which is in Netherlands, it will go to the Amsterdam DNS server with 2 milliseconds. So Anycast is like awesome for that kind of thing. It gives you other benefits, like if you need to fail over to another location, you can just withdraw your routes or down your BGP session, and takes a matter of seconds only before all the traffic is shifted to another provider. So for monitoring, we monitor from multiple providers. So these servers would probe the edge servers to check whether their HTTP server is running, whether there's any packet loss to them. And if the edge server has multiple IPs, we need to monitor all of those IPs, because if a provider happens to null root one of the IPs, well, it's not good if we were to send visitors there. And passive monitoring is the edge server sending UDP packets to our DNS servers about their utilization. So from what I said earlier, the load and the network bandwidth mostly. Further on, for monitoring, we use Manin for trends and charts, so that you can see historically what has this edge server been doing, and possibly correlate it with any other events that could have happened. We have Nagios to monitor individual services in our CDN core, which is the admin thingy. So for us, the worst thing that can happen is that traffic doesn't get delivered. It's like really the worst thing that can happen. And the way we've designed our system, it's loosely coupled so that the admin thingy is not coupled together with the DNS and edge server. So the admin thingy can be totally down. Parts of the DNS servers can be down, or parts of the edge servers can be down, but at no point would the whole network be down. We also have another kind of monitoring check called end-to-end checks. So whereas the Nagios checks check very specifically on some services, we find that we have to write many checks in order to get a good coverage of those every service. So instead, we to capture a broader range of errors, we write end-to-end checks which simulate and verify critical CDN activities. For example, for us, we would subscribe to all the Federation CDN POPs and create a CDN site, and on all those POPs, and make a request to all of them. And finally, we check whether those servers have reported that the bandwidth has been delivered, because it's super important also that we account for all the traffic on the CDN. Otherwise, we don't get money and our customers don't get any money. And these alerts are integrated with Tulio, which will give us a phone call if there's anything wrong. And I think this is my last slide, which is logging. So yes, so just like Gareth, we really like centralized logging. We just do this with plain syslog, not doing it with cloud services. The important thing I find about system logs is that they are most valuable when the system does go down. So if you have a storage problem, or if you have an out-of-memory problem, sometimes the only way you can diagnose it before it comes back up is to look at your logs, which the server may hopefully have sent to the central logging server. We also send our application logs only, not the system logs, to Splunk. It's just an experiment to try to see whether it how it fits us. So over here I have a chart which shows our internal SLA is 300 seconds, but we're actually performing at more like 400,000-ish, which means that we are violating our SLA. But that's not it's not about violating the SLA that's the problem. It's more like we are aware of it, and that's the important thing. So we did a deployment last week where the behavior of the code changed, and it took 100 seconds more on average to produce this edge configuration and DNS schedule. So like this tells us that it's something that we need to look into. It's not super urgent, but yeah, we do need to look into it. So for our edge servers, we have a sample of access logs and error logs that we send to our central log server. So by sample, I mean we take like we take up to 100 per second from the servers, because if we take everything, we would have to store billions of request logs every single day, and there'll be a lot of storage overhead, a lot of network overhead, so we don't want that, so we just take a sample. It's enough to do like troubleshooting if there's some sort of CDN problem, like your edge server can't connect to the origin, or there's some sort of weird caching problem. So okay, thanks, and We're looking to hire as well, so if you're eager, just let me know or just write to me. Okay, thanks.